What if the next soldier on the battlefield has no pulse, no fear, and never sleeps? This is the machine already changing modern war. Unmanned ground vehicles are already patrolling borders, clearing minefields, and hauling ammunition into combat zones without a single human inside. An unmanned ground vehicle, or UGV, is any wheeled or tracked robotic system built to operate on land without a person aboard. The concept began nearly a century ago, with radio-controlled demolition tanks used to clear obstacles under enemy fire. Decades of advances in electronic sensors and computing power transformed crude remote tanks into today's intelligent robotic platforms. Modern UGVs are grouped by size and mission: small reconnaissance units, medium logistics carriers, and heavy armored combat platforms. The smallest UGVs are built for reconnaissance, slipping into collapsed buildings or tunnels too dangerous for any person to enter. Explosive ordnance disposal robots use precision manipulator arms to inspect, isolate, and neutralize dangerous devices safely. Larger logistics UGVs carry ammunition, water, and equipment across difficult terrain, reducing the need for exposed human supply. At the heaviest end are armed combat UGVs, engineered to carry weapon systems directly onto the front line. Every UGV depends first on perception, using sensors to build a constant, detailed picture of the ground around it. Optical cameras, thermal imagers, and radar units work together, letting these machines see clearly in daylight, darkness, or heavy smoke. LIDAR sensors fire thousands of laser pulses per second, generating a precise three-dimensional map of obstacles in real time. Proximity and ultrasonic sensors line the chassis, allowing the vehicle to detect nearby obstacles even in its immediate blind spots. Combining these sensors lets a UGV distinguish between solid ground, loose debris, and impassable terrain within milliseconds. All of this sensor data feeds into an onboard computer, the true decision-making core hidden inside every UGV's armored hull. This onboard processor filters raw sensor input into usable information, identifying paths, obstacles, and potential hazards continuously. Terrain classification algorithms let the vehicle adjust speed and traction automatically when crossing sand, mud, or broken rock. Communication antennas keep the UGV linked to human operators, relaying video, telemetry, and status data across the battlefield. Operators watch this feed from a safe location, sometimes kilometers away, guiding the vehicle through a live video and data link. Mobility is the second core challenge, and engineers choose between tracks, wheels, and even legs depending on the mission. Tracked systems spread weight evenly, giving UGVs excellent traction across mud, snow, and uneven battlefield terrain. Wheeled UGVs sacrifice some traction for speed and efficiency, making them better suited to roads and hard-packed ground. Independent suspension systems let each wheel adjust individually, keeping the chassis stable even on jagged, uneven surfaces. A newer generation of legged UGVs can climb stairs and cross rubble that would stop any wheeled or tracked vehicle entirely. Hydraulic and electric actuators inside each joint allow precise, adaptive movement across the most unpredictable ground conditions. Engineers test mobility systems relentlessly, forcing each design through obstacle courses that mimic the chaos of real combat zones. Specialized tread and tire designs are engineered specifically to maximize grip on sand, gravel, ice, and broken pavement. Climb angle testing ensures a UGV can ascend slopes as steep as 45 degrees without losing traction or stability. Sealed, waterproof housings allow many UGVs to ford shallow rivers and streams without damaging their internal electronics. Power systems define how far and how long a UGV can operate before returning for fuel or a recharge. Purely electric UGVs are quiet and low heat, ideal for stealth reconnaissance where noise could reveal a position. Hybrid diesel-electric systems extend range significantly, generating power on the move rather than relying only on stored batteries. Heavier combat platforms often use diesel engines directly, trading quiet operation for greater range and towing capacity. Some smaller surveillance UGVs even integrate solar panels, allowing indefinite loitering in remote observation posts. Thermal management systems keep batteries within a safe operating range, preventing overheating during sustained high-power missions. Experimental hydrogen fuel cells are also being tested, promising longer range with a far smaller logistical fuel footprint. Efficient power distribution ensures sensors, communications, and mobility systems all draw energy without overloading the platform. Field-swappable battery packs mean a depleted UGV can return to service within minutes rather than hours of downtime. This balance of power source and mission profile is critical since a stranded UGV becomes a liability rather than an asset. Communication links are the lifeline connecting every UGV to the humans who ultimately decide how it operates. Encrypted radio and satellite links transmit video, sensor data, and commands, protecting the connection from jamming or interception. Because these links can be jammed or severed, engineers design UGVs to handle sudden communication loss safely. When a signal is lost, most UGVs are programmed to stop, hold position, or retrace their last known safe path. Operators can choose between direct teleoperation and supervised autonomy, adjusting how much control the machine handles itself. In full teleoperation, every movement is directly commanded, giving maximum control but requiring constant human attention. In supervised autonomy, the UGV navigates independently toward a destination while a human monitors and can intervene at any moment. Onboard artificial intelligence processes sensor data locally, allowing critical navigation decisions, even if the communication link drops entirely. Path planning software calculates the most efficient and safest route in real time, constantly recalculating as new obstacles appear. Some systems now coordinate multiple UGVs at once, maintaining formation and spacing without a single vehicle needing individual piloting. For combat variants, the remote weapon station is the most heavily engineered component on the entire platform. These turrets allow a human operator to aim and fire from a protected position, far from the point of contact. Stabilization systems keep the weapon steady, even while the vehicle itself is moving across rough and uneven terrain. Targeting systems combine optical zoom, thermal imaging, and laser rangefinding to identify and track objects at long distance. Every firing decision on an armed UGV requires deliberate human authorization, a safeguard built into current military doctrine. Automated ammunition feed systems allow sustained fire without requiring anyone to physically reload the vehicle in the field. Not every weaponized UGV is lethal. Some are equipped with non-lethal systems for crowd control or perimeter denial. Armor plating protects the vehicle's critical systems from small arms fire and shrapnel during close engagements. UGVs are increasingly tested in urban environments, where visibility is limited and threats can emerge from any direction. Beyond combat, logistics UGVs solve one of warfare's oldest problems, moving supplies across terrain too dangerous for trucks. A single resupply UGV can carry hundreds of kilograms of ammunition, food, or medical supplies to forward positions. Casualty evacuation UGVs are designed to retrieve wounded personnel from exposed positions without risking additional lives. These platforms include stabilizing mounts and smooth. Each flail strike clears a safe path meters wide, allowing personnel and vehicles to follow without stepping on hidden threats. Ground-penetrating radar allows some UGVs to detect buried explosives before ever making physical contact with the ground. This mapped data is shared instantly, marking confirmed safe corridors for every unit operating in the area. Border and perimeter security UGVs patrol continuously, using thermal cameras to detect movement across long stretches of open ground. Thermal imaging lets these sentries operate around the clock, regardless of darkness, fog, or adverse weather conditions. Swarm robotics represents the next major evolution, coordinating dozens of small UGVs as a single distributed system. Mesh networking allows each unit in a swarm to share data instantly, extending awareness far beyond any single vehicle's sensors. This distributed approach makes swarms resilient, since the loss of one unit does not compromise the overall mission. Commanders can monitor an entire robotic formation from a single interface, adjusting objectives as the situation develops. Cybersecurity is a constant concern, since a hacked or spoofed UGV could become a serious liability on the battlefield. Layered encryption, authentication protocols, and signal verification all work together to prevent unauthorized control of these machines. Global positioning systems provide baseline navigation, but battlefield jamming often forces UGVs to rely on backup methods. Inertial navigation systems track movement using internal motion sensors, keeping the vehicle oriented even without satellite signal. Simultaneous localization and mapping software lets a UGV build its own map while navigating unfamiliar terrain in real time. All of this computation happens on board within milliseconds, allowing the vehicle to react faster than a human operator ever could. Before deployment, every UGV design undergoes years of rigorous testing across extreme climates and punishing terrain. Environmental chambers simulate desert heat, Arctic cold, heavy rain, and dust storms, exposing weaknesses before real deployment. Structural stress testing pushes each frame to its mechanical limits, ensuring reliability under the punishment of real combat. Engineers analyze thousands of data points from every test run, refining software and hardware with each iteration. Once validated, successful designs move into production, with growing numbers of nations fielding their own UGV programs. Live exercises integrate UGVs alongside conventional vehicles, testing coordination between robotic and traditional battlefield systems. Maintenance remains a major factor since complex sensors and actuators require specialized care to stay mission-ready. Modular designs let a single chassis switch between reconnaissance, logistics, or weapons payloads depending on mission requirements. This flexibility reduces cost, allowing militaries to adapt their robotic fleet without building entirely new vehicles. Research continues into greater autonomy, better power density, and more resilient communication for the next generation of UGVs. Emerging battery technologies promise longer missions with lighter platforms, extending how far a UGV can operate unsupported. Future systems aim to coordinate UGVs directly with aerial drones, sharing data. Whether patrolling borders, clearing mines, or hauling supplies, unmanned ground vehicles are steadily reshaping how militaries operate. From reconnaissance scouts to armored combat platforms, each design reflects the same underlying goal: reducing risk to human life. As sensors, power systems, and autonomy continue advancing, these machines will only become more capable and more widespread. The unmanned ground vehicle began as a simple remote-controlled tool and has become a defining feature of modern military engineering. Its story is still being written, as machines increasingly take on the danger so that fewer human lives ever have to.